Hello and welcome students to another lecture on ionic bonding. And this time we're going to go ahead and cover a concept that should hopefully be something that you guys want to get to here, which is going to be the concept of the transition metals with ionic bonding. So before we ended up saying that, this row was 1, this row was 2, and then we skipped all of these. And we didn't just skip this group right here, but we also skipped all of these. And if you notice, the area that we ended up skipping made up a majority of the table, okay? And the reason that we skipped this group is because this group is what's known as the transition metals. And the transition metals are metals that have a variable loss of electrons, okay? So these metals right here, these ones that are right in the middle, this entire group of transition metals, and both the lanthanides and the actinides are all metals that can change. And let's go ahead and go into the dark mode. Okay, let's go here. These are all, oh no, that's probably going to show up terribly, but we'll work with it for now. All these metals can have variable electron loss, okay? So that means that it's going to be harder for us to go ahead and tell. Now luckily, because chemists are lazy, we have an easy way to go ahead and identify that, okay? So we're going to start with iron here, and we're going to say that we have iron combining with another element. Oh, and let's go ahead and define here first, before we get too far, what a transition metal is. So a transition metal is a metal with a variety of oxidation states, okay? And oxidation states are just a variety of amount of electrons that it can lose. Have a variable amount of electrons that they can use. Okay. And another thing about that is that the different electron ions, or the different oxidation states, are also going to end up having different properties as well. So for instance, right here, this image that we have here is an example of a couple of the different oxidation states and the colors that they'll have. Titanium usually is +3 and it ends up being purple. But with a compound like vanadium, when you have a vanadium 2 solution, it's purple. When you have a vanadium 3 solution, it looks green. Vanadium 4 is blue and vanadium 5 is yellow, okay? So these different solutions will end up having a different color to them. Ooh, that would actually seem like it'd be a nice lab to do. Go ahead and identify the oxidation state based off of the color. That seems like a nice lab. Maybe I can work that up. So the different colors are going to mean that it's going to interact differently. It's also going to change how it bonds, okay? So what we're going to do is we're going to go ahead and take iron, and we can see that iron has both +2 and +3 varieties, okay? And we're going to bond iron, okay? And we're going to say that we're going to have iron combining with oxygen, okay? So this is our plan. When we're writing this out, we're going to have to write the formula for it, okay? And the formula for this is going to be iron 3 oxide, okay? And now this 3 that's here, that's going to indicate the charge. So this iron 3 is really this iron 3, okay? So it's this +3 iron that we have, okay? So that means that when we go through our process of figuring out what the formula is going to be, this 3 is directly going to relay to 3+ right here. And then we'll go ahead and add that to oxygen, and we can take a look. Oxygen here is in the 6th row. So that's going to be 2 minus. Therefore, this compound here, when we figure out the formula, is going to be Fe2O3. Because the 3 that was here on iron got moved over to the oxygen. Okay? And that's all that it really is. It's really just saying, hey, this Roman numeral right here is going to be the oxidation state for that particular metal. Okay? Now let's go ahead and go backwards, and let's go ahead and pick another one of these metals here. And let's pick, chromium. There we go, chromium. 6+. So let's say that we have chromium 6 chloride, okay? So let's go ahead and take a look at what that formula would be. So we'd go ahead and write out chromium, and this is the Roman numeral for 6 chloride, okay? Which means that we're going to go ahead and write it out as Cr. And since this is 6, this is going to be 6+, because this is the one that we're working with right here. And that's going to be combining with chlorine, and that's -1. We'll go ahead and crisscross them. We'll have Cr1Cl6, and then we always want to go ahead and drop the 1. Okay, and we'll be left with this compound right here. All right, so see, in a way this is even easier because you don't even have to count. Okay, now I'm gonna warn you, this is the one that most often I have students have issues with. But this one, you don't even have to count. Like, it literally tells you the number on it, okay? Now, for those of you that aren't familiar with your Roman numerals, okay, this is 1, this is 2, this is 3, this is 4, this is 5, 6, 7, and then 8 is 1, 2, 3. Okay, and you should never need more than that, to be perfectly honest, all right? Now, in the transition metals, there are going to be a couple that I will forget, that you do not, necessarily know offhand, that they do not have variable oxidation numbers. And there are going to be 3 that show up just frequently, all the time. The 3 that we're going to be worried about is silver. Silver has only 1 oxidation state, so silver will only lose 1 electron. Zinc also only has 1 oxidation state. It's only going to lose 2 electrons. So every time you see zinc chloride, that's always going to have 2 electrons missing. And the last one is going to be cadmium. That's going to also have 2 electrons lost every single time. Okay, that's really it for transition metals. One thing to note is that the transition metals also include these right here. Even though they seem like they're special, they end up being the same type of deal. Uranium, if we click into uranium here, hopefully it'll let us click into it. Uranium is another one of those that it can have many oxidation states. Let's go ahead and see how many it has. It can be 1, 2, 3, 4, 5, or 6. Okay, so uranium can have up to 6 different oxidation states. So all these ones down here also apply to this rule. So just because it seems like it's down here doesn't mean that it's not going to follow it. Okay. The only issue that I have with giving you any of these oxidation states is, so for instance, like lawrencium, like you're never going to encounter lawrencium because it's so, here it even says that it has +3, but we don't even know if we can get something else. Lawrencium exists at such a rarity that we're never going to be able to test to see what all the different oxidation states are. All right. So that's just something to be aware of, that this is how we go ahead and indicate which oxidation state it's going to be, is going to be indicated always in the actual name of the compound. And then later on we'll get to go ahead and figure out how to do this process in reverse. If I'll give you a sneak peek, since this chlorine is 6 and had a charge of 1, the 6 goes to the chromium. Alright, but for now we'll go ahead and close out, and I hope you all have an easy time with the worksheet. It should be nice and short and to the point for you. And remember, if all else fails, be lazy.